Okay, I guess we should start the talk. So I'm very happy that Andrés Vindas Meléndez will give a talk today. So he's talking to us from the University of Kentucky, and he's going to just talk about decompositions of Ehrhart H-star polynomials for rational polytopes. Take it away.
Awesome. I know some of you have heard part of this talk, or a fast version of this talk, I should say, but hopefully I'll be a little slower this time. So thank you for the invitation. I'm happy to talk to you about this project that I just got my reviews from in the journal today, actually, that I haven't decided not to look at. And so I think they're good. But in any case, this is joint work with Matthias Beck, who's a professor at SF State and currently at FU Berlin, and Ben Braun, my PhD advisor at University of Kentucky. And so what are the main characters? The main characters are now rational polytopes. So if you were in the pre-seminar, you probably saw we were talking about lattice polytopes, but now I'm going to care about rational polytopes. And so I'm going to let P be a rational polytope. And what I mean by that is I'm taking the convex hull of finitely many points in Q to the D. Okay. So the vertices are now rational points as opposed to integral points. Okay? And for a positive integer T, I'm going to let L sub P of T denote the number of integer lattice points in the teeth dilate of the polytope P. Okay. And so at the pre-seminar, I said that that Ehrhart proved this theorem for lattice polytopes, but in fact, I think he did something a little bit stronger or more general, is that if we're given a rational polytope, P, the counting function is actually a quasi-polynomial of this form, okay? Where now we don't have coefficients, but we have these periodic functions. Okay? And so we call this the Ehrhart quasi-polynomial. And each period divides the denominator Q of P. And so I'm defining the denominator to be the least common multiple of all vertex coordinate denominators. Okay? So this is a mouthful, but I'll give you examples in just a little bit. Okay? So you might ask yourself, well, Andres, I still don't know what a quasi-polynomial is. So here's another definition of what a quasi-polynomial is. A quasi-polynomial is a function from, let's say, Z to R of that form, where you have periodic functions in variable T. And then you might still say, well, Andres, that's not as helpful. And so you could also think about a quasi-polynomial as kind of a set of polynomials depending on your period, okay? And just as we did for the lattice polytope case, we can encode this quasi-polynomial in a generating series. And so we get the Ehrhart series. And so it turns out that the Ehrhart series now can be written also in this nice rational form. Only now that we have this Q to the D business popping up, right? So we're keeping track of this denominator. And I will also add that this rational form is not in lowest terms, okay? But I do want to just be consistent in keeping it in this form. Yeah. Awesome. And so we call again the numerator of this the H star polynomial of P. And so what is maybe an example? Let's do a small example. Oops. My bad. Should have turned off my phone before. And so let's do this a small example of the convex hull of -1 half 1, -1 half -1, 1 half 1, 1 half -1. And so maybe you can visualize what this is. And if you're quick, you can kind of tell yourself or convince yourself that this is a rectangle, right? And notice that the vertices, again, are not integral points, but it does have some integer point or integral points, lattice points inside the polytope, okay? And so Ehrhart theory, we care about dilating the polytope. So we are going to dilate by integral factors. And so here's P, here's 2P, 3P, and 4P. Yeah. And the lattice point and numerator is a quasi-polynomial. And so first, we note that this has period 2 or denominator 2. Again, the denominator is the least common multiple of all vertex coordinate denominators, so it should be 2. Kind of telling us that we should anticipate that our Ehrhart quasi-polynomial has kind of two polynomials popping up. When t is even, we get this. When t is odd, we get that. Yeah, nothing crazy here. And now when we encode it in the, or when we get the Ehrhart series, we do this business, all the algebraic manipulations and stuff. And now what I'm gonna care about is decomposing the H star polynomial for rational polytope. So in this case, let's look at this H star polynomial. And one thing that you might note in this particular example is that the H star vector, meaning I'm just pulling the coefficients out of the polynomial, is palindromic. And so hopefully at the end of the talk, and if I don't, somebody remind me, I'll give you an answer as to why in this example, we have a palindromic H star polynomial. Yeah, everybody with me? Awesome. Okay, and so maybe some facts or some known results about rational polytopes. So again, we have these reciprocity results. And so we have Ehrhart-McDonald reciprocity for rational polytopes. And so if we have a rational polytope, the lattice point enumerator evaluated at negative t enumerates the number of integer lattice points in the interior of P up to a sign. Yeah. And similarly, we have this reciprocity result for the Ehrhart series. Okay. In the 80s, Stanley proved that if you have a rational D polytope with the following Ehrhart series, the coefficients of the H star polynomials are non-negative. Okay. And so the decompositions of the H star polynomial for rational polytopes that I present in a little bit are kind of another way to look at the non-negativity result by Stanley. And also by Stanley is his monotonicity result. And so if you have a polytope, a rational polytope P contained in a larger polytope Q, and we can dilate it big enough so that we can get them to be integral, his monotonicity result says that the H star polynomial of Q, the coefficients of H star polynomial of Q dominate the coefficients of the H star polynomial of P. Okay. And so what are my goals for this talk? It's to present you a generalization of a decomposition in the lattice polytope that was proven by Betke and McMullen in the 80s for the lattice polytope case. Okay. And we're going to use this decomposition somehow to provide another proof of Stanley's monotonicity result. Okay. And I'm going to present to you a generalization of the H star polynomial for lattice polytopes, also due to, well, this one's due to Stapledon in 2009. And I'm going to present to you an application of this decomposition, which hopefully will give a partial answer as to why that first example gave a palindromic H star polynomial. Okay. So first, let's do some setup and notation. Oops. I'm trying to move so that I can see some of you, but I can't. Okay. So a rational pointed simplicial cone is a set of this form, where W is the set of linearly independent vectors in Z to the D. Okay. And so I'm also going to define an open parallelepiped associated to that rational pointed simplicial cone as this. Okay. And I'll give you examples, small examples in a little bit. And then the last thing before the next slide is I'm going to denote by U a projection onto the last coordinate. And from there, I'm going to define a box polynomial as being the sum of Z to the U of V, where V are the integer points inside my box. Okay. Now you might say, Andres, that is confusing. And so here's a small example. And so let's let W just be 1, 3, and 2, 3. Okay. So then my box should be of this form. Yeah. Well, what does that look like? It looks like this. Okay. And so it's an open box, and so I don't care about the things on the boundaries, right? And I see that it has 2 integer points, one at 2, 4, and one at 1, 2. Yeah. And so the box polynomial should be, again, I'm taking the last coordinate of each of the integer points. So it should be z squared corresponding to this 0.12 and z to the fourth corresponding to this 0.2 comma 4. Yeah, everybody with me? Okay. I'm also going to define the fundamental parallelepiped to be the half-open variant of the box, okay? And so this is the mathy definition, but again, this is now I'm just taking part of the boundary in the open and of the parallelepiped, yeah? Okay. I also care about coning over a polytope. And so if I have a rational polytope with vertices, let's say V1 through Vn, we're going to lift them one dimension higher by appending a 1 to the last coordinate. Okay, so that's what this cone looks like. Well, that's what this cone is. And what does that look like? Well, it looks something like maybe like this. Yeah, where if at a certain slice, I can recover a dilate. A slice of the cone, I can recover a dilate of my original polytope. Yeah. Awesome. And so I'm going to say that a triangulation T of a D polytope is a subdivision of P into simplices of all dimensions that is closed under taking faces. And so I care about triangulating a polytope, and I'm counting all the simplices, and so of every dimension. And so here's a triangulation of the original example that I showed, right? And this has 4 two-dimensional simplices, and it has 8 one-dimensional simplices. I did not prepare this one in advance, and it should have 4 zero-dimensional simplices, and we're also going to count the empty face as a simplex. Yeah. And so now I'm going to define the denominator of a triangulation to be the least common multiple of all vertex coordinate denominators of all faces of the triangulation. Okay. And here's an H polynomial of a simplex with respect to the triangulation. And actually, to answer Rohan's question, which I will say Isabella is right, if you have an H star polynomial, the H star polynomial of a polytope that admits a unimodular triangulation is equal to the H polynomial of the triangulation. Yeah. Okay. And so one thing that I will note is that when we consider boundary triangulations, I'm bringing this dimension actually one less, okay? And so for a simplex with denominator, let's say P, again, we're gonna let W be the set of integral ray generators of cone at height P, and we're gonna define the H star polynomial of that simplex to be the generating function of the last coordinate of integer points in the fundamental parallelepiped, okay? So I'm not saying anything crazy, I'm just saying, okay, if I have a simplex, I take its fundamental parallelepiped, and now I'm just gonna care about the integer points in the fundamental parallelepiped, and that should give me the H star polynomial of that, okay? All right, and I can't see, okay. So now let's do the decomposition according to Betke and McMullen, or our rational generalization, okay? So we have a rational polytope P, and we're gonna triangulate it. We have a triangulation T with denominator Q. For a simplex in the triangulation, I'm gonna let W be the integral ray generators now at height Q, right? Where Q is again the denominator. This is just some notation. Instead of writing B of every W, I'm just gonna write B or the box of the simplex, okay? So we need a little lemma. So if we fix a triangulation T with denominator Q, then the H star polynomial of the H star polynomial of a simplex in the triangulation is equal to the sum of the box polynomials of every simplex in, or sorry, every kind of so we have a simplex, and we're taking each of the parts of the simplex, so every subsimplex. And so let me show you the sketch, and maybe it'll make clear what I mean by that. So first, we want to show that the fundamental parallelepiped of the simplex is the union of the boxes of all subsimplices. And so here, let's just take the simplex to be this line segment, right? Here is our fundamental parallelepiped. And so we're going to take all half open. Sorry, man, I should have really turned off my phone. My bad. And so here is the box, or yeah, so we have the simplex, our original simplex, and we're taking the fundamental parallelepiped, and we're taking all boxes corresponding to the subsimplices of this of my original simplex. Okay. Yeah. And so now the H star polynomial of that simplex is just adding up the corresponding parts. Okay. I'm not saying anything super crazy here. I'm really just keeping track of all this information. Is everybody with me? Yeah. Okay, so what is the decomposition? And so if I, again, do the same business, I have a triangulation T with denominator Q of a rational polytope P, then the Ehrhart series is now a sum, or the H star polynomial is a sum of these box polynomials times these H polynomials, okay? And I should say that that this is why I like this is because it brings together the arithmetic data from the simplices from a triangulation and combinatorial information coming from the structure of the triangulation, okay? And so I'm gonna run through a little sketch of a proof. So we write P as a disjoint union of all open non-empty simplices in the triangulation, okay? And so we should get our Ehrhart series to look something like this, right? It's just, I'm adding up now all the Ehrhart series of my open simplices, okay? I'm going to apply Ehrhart-McDonald reciprocity. And then by my previous lemma, right, I have now just everything is half open, or sorry, open simplices. And so I'm applying the previous lemma. And one thing that I left out is that the box polynomials actually is not very difficult to see because the box polynomials are things with just coefficient 1 and keeping track of the integer points, but there is some symmetry to the box polynomials. And so using that, and then I'm applying the definition of the H polynomial. And so again, I'm doing all of these things for each open non-empty simplex, okay? And so for each part, I'm taking the box polynomial for the stuff inside it and doing the H polynomial, okay? And with that, I put it all together and I get this decomposition, okay? And so yeah, so this is, again, it's a decomposition of the H star polynomial where it's keeping track of the data coming from the simplices and the triangulation. Sorry, the integer points of the the integer points coming from the boxes of the simplices and the H polynomials of the triangulation. Okay. Any questions so far?
Sorry, in the numerator there, is that the H polynomial of the simplices or the H star, your H of omega ZQ?
This is an H polynomial. It's the H polynomial of the that's coming from the triangulation that I showed, the definition that I showed earlier. I can go back to it.
The ordinary H polynomial?
It's this one.
I'm a little confused about what omega is while we're at that.
So omega is these, sorry, I should have been a little bit more clear. It's every half open, so in this case, for example, if I have the line segment, yeah, it's every half open simplex in the fundamental, in the box. And so if I have this line segment here, yeah, and I take the fundamental parallelepiped, I'm going to say this is one part, this is one part, this vertex is one part, and then whatever's inside.
Okay, thanks.
Can I ask another question? So how do you compute the H vector? So the H vector of usual simplex is usually just, if it's the boundary, then it's all ones. If it's the whole simplex, it's one and bunch of zeros. But here it's half open, half closed. So how do you compute the H vector here?
So I mean, I'm really just following this definition, and I'm keeping track of every simplex. So it's every simplex in the triangulation of my original polytope. And so I think maybe I have an example of this actually. Let me see. I do not. But in my other decomposition, I still use this H definition, H polynomial definition. And so maybe we can come back to it, and I can show you exactly how I'm computing it, because I do have an example for the next decomposition.
So is it something like the H polynomial of the relative complex?
This is where I always mess up. And I think this is, who's talking, Steve?
Yeah.
I emailed you, I think, yeah, a while back, I think asking about these things. And so, yeah, I'm in that's terminology that I'm not super aware of, but that does sound right. And I think this next lemma that I will show, I think might answer your thing, but yeah, I think I have a lemma, and then maybe you can tell me if what you were thinking is right. And so I want to now use, I mean, that Betke McMullen decomposition was not too difficult to do. It was just kind of pushing through the appropriate pieces. And actually, one thing to note is that these box polynomials and H polynomials all have non-negative coefficients. And because we're summing non-negative coefficients, then this is kind of a different roundabout way to see Stanley's non-negativity result. Okay. What I want to do is kind of now use the Betke and McMullen decomposition to prove Stanley's monotonicity result. Okay. And so again, if we have a polytope P contained in a larger polytope Q, and they're both rational polytopes where when we dilate them big enough, we can get them to be integral, or get them that Q dilate to be integral, then we define the H star polynomials as follows, right? And what this is saying is coefficient-wise, the H star polynomials, the H star coefficients dominate the H star coefficients of P. Okay. And so here's an example. I'm saying Q is this tetrahedron, right? And P is this kind of this bottom triangle, right? And here I've computed the H star polynomials. And what I'm saying is these will dominate the coefficients of in coefficient, right, in each position. Yeah. Okay. And so I think this is the lemma that I was kind of talking about, Steve. So if I have a polytope P with a triangulation T, right? And I'm going to say, well, P is contained in Q, and T prime is the triangulation of Q. And I want it to be such that when I restrict to P, sorry, let me start over. I have a polytope P and a triangulation T of P, right? So I'm going to let P be contained in a larger polytope Q, where T prime is the triangulation of Q, such that T prime restricted to P is my triangulation T, okay? And so one thing that I wasn't keeping track, or that I had a hard time thinking about, is when the dimensions of P and Q differ, right? And so I'm going to assume that there exists some set of affinely independent vertices of Q that are outside the affine span of P, such that one, the joint of T and the convex hull of those vertices is a subcomplex of T prime, and the dimension of P join the convex hull of those vertices equals the dimension of Q. Okay, and so for every face in my triangulation, the coefficient inequality holds. And so this is kind of giving me now the kind of the monotonicity of the H polynomials coming from these triangulations. Okay. And so maybe here's a picture kind of to illustrate what I mean, is that here's Q, and I'm going to say Q is the hexagon, P is just this line segment, yeah, and T, the purple, is my triangulation of T prime, yeah. Also, yeah, well, considering these full dimensional simplices, when I restrict to just P, turns out actually the line segment was the triangulation with one simplex and two zero simplices and the empty face. Yeah? What the lemma is saying is that the H polynomial of this triangulation for every again, keeping track of every simplex, dominates the H polynomial here. Okay. Everybody with me? Okay, awesome. And so now it's essentially putting all the pieces together. Again, this is the same business, the same scenario as before, right? We have T prime, triangulation of a polytope Q. When we restrict it to P, it gives us the triangulation of P. Yeah? So by the rational Betke and McMullen result, we kind of know what the H star polynomial should look like. Yeah. Since P is contained in Q, it's saying, okay, well, now we care about the stuff, the stuff with just Q, and the business with P. Okay. By the previous lemma of the what should I call this? The monotonicity of the H polynomials. Now I can say that this part here should dominate the coefficients coming from just the relevant stuff in P. Okay. And now putting it all together, I get my desired inequality saying, okay, well, this is the stuff coming from P, and this is the stuff coming from Q. Okay. So it's very wordy, but it really is just following all the appropriate steps and making sure that I have the right inequalities. Okay. And so this gives a different proof to Stanley's monotonicity theorem. And I will say that Stanley's original proof was very algebraic. And while I think our lemma relied a little bit on Cohen-Macaulay complexes, which again, I wasn't super, I think I talked to you, Steve, and I talked to also to Jose Samper about these things. I think, yeah, I want to say that our proof is less algebraic than what Stanley originally did. Okay.
So can you think of this? So you have this product of box polynomials times H polynomials.
Mm-hmm.
So should that be viewed as something like the box polynomials are capturing the coordinate geometry and the H polynomials are capturing the combinatorics, and you can sort of decouple them from each other?
That's right. Yeah. So the box polynomials are just keeping track of the data coming from the integer points in these boxes. And so it's like this arithmetic data. And the H polynomials is keeping track of the information that's coming from the triangulation. So what you said is essentially right.
I'm sorry, can I see that H polynomial definition again? I'm still confused by it.
Yeah. Just a second. Oh, that was a little bit further. Yeah.
So is that the H polynomial of the link?
Oh, yes, that's right. It's the H polynomial of the link.
Oh, okay.
Yeah, I should have made that a little bit clearer. This is the H polynomial of the link. Yeah. And I hope, yes, that's right. It's the H polynomial of the link. hopefully that resolves some of my confusion that I gave onto you. But it is the H polynomial of the link.
Okay, thanks.
Okay. Are there any other questions? Those are good questions, and I apologize for confusions. No other questions? Okay, awesome. So now I want to give a decomposition of the H-star polynomial coming from a boundary triangulation. Okay, so again, I'm going to fix, well, in this setup now, I'm fixing a boundary triangulation. And so in that H polynomial, I have to keep track that I'm bringing it one dimension lower. Okay, and so in this case, I'm going to take an integer point, positive integer point, L, such that my L dilate of my polytope P contains a lattice point A somewhere in its interior. Then I'm going to, so again, I'm coning over my polytope such that A comma L lies somewhere in my cone, okay? And then I'm gonna say, if I cone over just that point, I get a ray coming from the origin of my cone through that point, okay? And again, I'll have a small dimension picture in just a bit. Okay? So again, we're coning over each simplex in our triangulation. And so for each simplex, again, I'm taking my W to be the set of integral ray generators at height Q. Okay? And so this is, again, almost the same setup, only that now I have this W prime. And what that W prime is, again, is my integral ray generators union that point that I am specifying, okay? And so I want to say that each point in the cone can be uniquely expressed in this form. I think I want to skip over these details, but I'll show you the decomposition. So I'm going to consider a rational polytope that contains an interior point A over L, right? Or when I'm taking the cone, I can consider A comma L, right? Where A is in Z to the D and L is some positive integer. I'm fixing a boundary triangulation with denominator Q. And so then this is the decomposition of the H-star polynomial that I get. Okay. And so, right now it's a sum of box polynomials coming from each simplex in the triangulation. And now I have to worry about the stuff that's coming from unioning that specified point, okay? So here's an example. Let's just consider the small line segment 1/3, 2/3. So that's this small line segment over here. Again, I coned over it, so now I'm in ambient space 2. The boundary triangulation has denominator 3. Again, the denominator is the least common multiple of the least common multiple of vertex coordinate denominators. So that should be 3. Yeah. And again, when I dilate my rational polytope by the denominator, I will always get a lattice polytope. So here's the third dilation. Okay. I'm going to take my A comma L to be 2, 4. So that should be this point here. So that's what I'm specifying. So what are my simplices in the triangulation? Well, it's a boundary triangulation of a line segment. So I just have the empty face and the 2 vertices. Okay. So now I have to take my integral ray generators coming from each of the vertices. And so that's W1 corresponding to delta 1, W2 corresponding to delta 2. Okay. And I'll skip over this detail here. It's not that important. But now I'm keeping track of all this information, right? And so for each of the simplices, I go through and put everything together. So what is my dimensions? Well, my dimensions are coming from the vertices and the empty face. So it would be 0, 0, -1. Now let's look at the box polynomials of these things. And so again, from my box polynomial from here to here contains no integer points, right, in my first one. Also the same here, right? And for my empty face, I just have the origin. That's one. Now I have this box polynomial of omega prime. That means I care about the same integral rate generators of these box polynomials, right? With that point specified. And so I specified 2, 4. And so I should get that my box of omega prime, or I should say box of delta 1 prime, is this yellow one over here. And box of delta 2 prime is now this pink one over here. And you can also see that they're empty because I made this very small example. But the box polynomial of the empty face, which should just be this this box, contains 1 point, which is here. And this is the point 1, 2. So it's giving me z squared as the as my box polynomial. And then if you put the same information through the definition of the H polynomial, I get this. And so when I put it all together, this is the H star polynomial for this small example. And so you might say, okay, well, Andres, this is kind of a drag. Why is this important? And so sometimes it's easier to compute H star polynomials rather than computing Ehrhart quasi-polynomials. And again, we can just move backwards, right? We can move from Ehrhart quasi-polynomials to Ehrhart series. But if we have the Ehrhart series or the H star polynomial, then it might be easier to move in the backwards direction. Awesome. Okay. So here's a proposition that I kind of want to mention just because it'll pop up in a little spot later. So if I have a rational polytope, again, denominator Q, and with this Ehrhart series, then the degree of the H star polynomial is S if and only if this here is the smallest integer dilate that contains an interior lattice point, okay? So nothing super illuminating, is only that we can, if we know the degree of the H star polynomial, we can tell you at what point or at what dilate will finally contain a lattice point, okay? So I want to turn our attention to this polynomial, which I call H star bar, which is taking the H star polynomial and multiplying it by 1 plus z plus all the way to z to the L minus 1, okay? And so, and again, we had that definition of, let me move back here. All I'm doing is I'm essentially moving this, I highlighted the whole thing, this denominator to this side, and I'm calling that H star bar, okay? Okay, and so one of our results is that the H star bar polynomial has a unique decomposition into what we call a symmetric decomposition or an AB decomposition, A of z plus z to the L B of z, where L is that first dilate where we see an integer point. Okay, that's what I'm calling L. And A of z and B of z are polynomials with integer coefficients that are symmetric. Okay. Furthermore, these coefficients, the coefficients of A of z and B of z are non-negative. Okay. And we use this H star bar decomposition to prove this result. And so I said, maybe in the pre-seminar, I said, okay, one open problem in Ehrhart theory is to classify all Ehrhart polynomials. Equivalent, you can say classify all H star polynomials for lattice polytopes. Well, what if that's in question is open, it's definitely open for classifying Ehrhart quasi-polynomials or Ehrhart H star polynomials coming from Ehrhart quasi-polynomials, or from rational polytopes, I should say. And that'll be very difficult, right? Because then we have to kind of keep track of the dimension and of the denominator, right? And if it's already open for dimension 3 in the lattice case, again, it's very difficult question. So what's the next best thing? So towards that classification, we can ask for inequalities that are satisfied by the H-star polynomial. And that's what this result is here is doing. And so if we're letting S be the degree of the H-star polynomial, again, L being that dilate where we finally see a integer point in the rational polytope, yeah, then the H-star vector of that rational polytope satisfies these two inequalities. And I will say that these are generalizations of two inequalities that were done independently by, well, one of them was done by Stanley and the other one was done by Hibi, Takayuki Hibi. And so I think, and again, both of these I think were done using very algebraic techniques for the lattice case. And so what we do here is generalize it for the rational case. Okay. And so now I want to end with a kind of an application of that last decomposition. So a lattice polytope is reflexive if its dual is also a lattice polytope. And so Hibi in the 90s proved this, he proved that if a lattice polytope is a translate of a reflexive polytope, if and only if the Ehrhart series satisfies this equality as rational functions. In other words, he proved that the H-star polynomial for the lattice polytopes are palindromic, okay, for reflexive polytopes. In 2008, Fisset and Kapschek proved that a rational polytope whose dual is a lattice polytope, so a rational polytope whose dual is a lattice polytope has palindromic H-star polynomial, okay? And so what did we do? Well, if we have a rational polytope containing the origin, the dual of a polytope is a lattice polytope if and only if in our H-star bar decomposition, the B polynomial is 0. In other words, the H-star polynomial is just equal to the A polynomial in the AB decomposition. And so in my very, very, very first example of the rectangle, I said, well, that one I showed you has palindromic H-star polynomial. And so it turns out that the dual of that polytope is a lattice polytope. And so when we do the H-star decomposition, which maybe I should have done it to be more illustrative, but I didn't, we would get that the B polynomial is 0. Okay. And so that, so this kind of gives a different way to approaching proving this result. Okay. And I think that is all I want to tell you. Thank you.
Let's thank Andres for an excellent talk. Any additional questions? Actually, can you show us the definition of that H polynomial once again? Just because I thought I understood, but then your example confused me again with 1 plus z cubed.
Yeah, give me just a second.
Sorry, I stopped your screen sharing there. It was so we could applaud appropriately.
Which one, sorry, Isabella?
The definition of the H polynomial once again.
Yeah, sorry. There it goes. Yeah. Yeah, so Steve is right that this is the H polynomial of the links.
So it's of the link of delta in T?
Of delta in T, yeah.
But T is kind of, so is T a simplicial complex or is it a relative simplicial complex? Because I'm kind of, so usually for simplicial complex, nice simplicial complexes, those things, if you encounter 0, then you never recover from that 0. But
Yeah.
somehow in your example, it was 1 plus z cubed.
Yeah, and so that example is, it might be coming from, again, the dimension here will have to be 1 less because we are considering.
Oh, so it's kind of a G polynomial of the length? If the...
Not exactly sure.
Wasn't the jumping coming from the fact that the denominator was 2, and so everything was in terms of z
For the
squared
last
in the
example that I
denominator?
showed? In,
Or am I misunderstanding your question, Bella?
Yeah, so in the last column, so the last bottom entry is
Oh,
1
I see.
plus z cube, right?
Yeah, I see.
And that's kind of mysterious.
oh, so one thing that I also would have to specify is
Oh,
coming.
you changed the variable. Okay,
changed the
okay,
variable.
okay, 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 okay. That explains things.
I'm changing the variable here because I have to keep track of the denominator.
Okay, vector 1, 1, I'm fine with as an H vector.
Yeah.
Thank you.
Awesome.
Any more questions?
I had a question.
Yeah, go ahead.
So when you have this palindromic polynomials, did you, these guys, did you try factoring them or complexes or over the integers even?
No, I haven't. So like, I haven't thought of questions about, I've not factored them. I have not thought about questions about like unimodality either. So like, those are all pretty open.
So I think it's worth trying the factoring and seeing if you have some, well, I like to factor actually. Sometimes when you have unimodal polynomials or these palindromic ones, you have this, what I call pretty factorization. So try and factor it into Q analogs of numbers. And you have to like force that kind of factorization because it's not irreducible over anything.
Yeah, I haven't thought about that, but I'll taking a note so that I can.
Okay, good. Yeah.
Yeah.
If it works out nice, let me know.
Yeah.
Sarah, is there an easy way to force that, or do you just have to kind of feed in a library to start dividing by?
It's almost like a library. I just try all the factors that are possible, right? Start with the largest possible one and just work your way down. But the other thing is Josh and I have a theorem, which is not yet, but if all of the factors are complex and sit on the unit circle or inside, then you should have a cyclotomic polynomial generating function thing. So that would mean that it has a nice factorization in terms of cyclotomic polynomials, which you might not see if you just eyeball it. But if you compare to the cyclotomics, then would be nice. But that would only be the case if the roots all lie on or inside the unit circle. So with regular Ehrhart polynomials, the roots lie on one half of the complex plane, right? That's the conjecture. But otherwise they're all over the place.
Yeah, I guess. Yeah, I'm not sure, but I know that Ben and Fu Liu thought about H-star polynomials on things that like are just in the unit circle. So.
Yeah. Well, maybe we should chat more about that.
Yeah.
Very cool talk. Yeah, thanks.
Thank you. Yeah, and I one thing that I did live out, and I guess I'll ask myself to tell you. Andres, tell them about one thing that he forgot to mention is we use this application to also to talk about what we are calling reflexive polytopes of higher index. And so Kastrick and Nil introduced some family of polytopes, and we were able to write the H-star polynomial for those families in small dimensions. Actually, I think it's only even in 2 dimensions for these polytopes, but there seems to be something like coming from, or there seems to be some period collapse in their Ehrhart quasi-polynomials that I haven't explored. So if anybody is interested in exploring Ehrhart theory and period collapse, I'd be happy to talk with you all also. That was a cheap plug for if you want to think about Ehrhart theory stuff with me, you're welcome to. Gosh, everybody's just, I never get calls. I literally never get calls. And today 3 people have called. Oh.
Maybe it's the same person. Any
No,
more
it's 3 different
questions?
people. It's 3 different people.
So if no more questions, let's thank Andres again.
Thank you all so much. Awesome. Well, thank you for having me. I hope that you all stay safe And hopefully we'll be able to see each other at some point in person in the near future.